Hello and welcome to the equilibrium unit explanation. Here we have the calculation of something called Kc. Well, Kc is your equilibrium constant. So this is a very valuable variable to be able to determine. It starts off with what's known as the law of mass action. So in this case, little a is the coefficient of big A. Big A is whatever molecule you want to be, and A is the coefficient in front of it, say 1, 2, 3, whatever. Same applies all the way through, so A plus B yields C plus D. So this is a classic double replacement reaction. So, like I said before, the little letters are your coefficients, and then the big letters are your atom, molecule, compound, base, acid, etc. And we'll be getting more to acids and bases later. Here you have Kc, and this is how you calculate it. The concentration of C raised to the power of its coefficient. Same with D, then all over A raised to its coefficient, and then B raised to its coefficient. And like I said, these are all concentrations, and you can tell because there's a bracket around them rather than a parentheses. Anywhere where you see a bracket, think concentration and think Kc as the base starting point. So here we have an example. NaNO3, sodium nitrate, plus HCl, hydrochloric acid, yields nitric acid and classic salt, NaCl. So, the Kc, the equilibrium constant for this equation, is HNO3, the concentration, raised to the first because the coefficient is 1, times the concentration of NaCl, divided by the concentration of sodium nitrate times the concentration of hydrochloric acid. This yields your equilibrium constant. Next, you have calculating what's called Kp, and that is your equilibrium constant for gases. You use the partial pressures to calculate this. The equation is very similar, only instead you have the partial pressure of gas C raised to its coefficient, the partial pressure of gas D raised to its coefficient, over the partial pressures of A and B raised to their respective coefficients. Like I said, this is useful for gases. Here we have the equation 3 Fe in the solid state plus 4 hydrogen in the gas, 4 water in the gas state yields ferrous oxide and hydrogen. Now remember, use only the gases. So for this particular equation, the Kp is simply just the partial pressure of hydrogen raised to its coefficient of 4 divided by the partial pressure of water raised to its coefficient of 4. Next, you have the relationship between Kp and Kc, your equilibrium constant based on concentrations and your equilibrium constant based on the pressure of the gases involved. This is determined by the equation Kp equals Kc times, in parentheses, RT raised to the power of the change in moles N. So, R in this case is the gas constant, 0.0821 liters times atm, your pressure, divided by mole times Kelvin, your unit of temperature. Obviously T for temperature equals Kelvin. And your delta N is your change in moles, so it's the mole of gaseous products minus the mole of gaseous reactants. Next, here's an example. 2 nitrogen monoxide plus oxygen yields 2 nitrogen dioxide. Given that the equilibrium constant based off of concentrations for this reactant at 290 Kelvin is 5.6 times 10 to the 12th. So you write out your equation, Kp equals Kc times RT to the delta N, and this equals 5.6 times 10 to the 12th times 290 Kelvin times 0.0821 liters atm divided by moles Kelvin to the -1, because there is 1 less mole of gas than there is to start with. So there's 2 moles of gaseous products and 3 moles of gaseous reactants, so to the -1. When you type all this into your calculator, you'll get a number where Kp is equal to 2.35 times 10 to the 11th. With significant figures for this, Kp equals 2.4 times 10 to the 11th. Your more complicated delta G in this case is equal to the negative RT ln K. In this case, R is the other universal gas constant, 8.314 joules divided by moles times Kelvin, and then yet again, T is your temperature in Kelvin. Now notice the negative sign, that's easy to be tripped up on. And your ln of K is the natural log of your equilibrium constant. So here we have another example. In a reaction at 298 degrees Kelvin, Kc equals 1 times 10 to the -6. Calculate delta G. So delta G equals the negative RT ln K. you substitute the numbers in, you get negative 8.314 joules per mole time Kelvin times 298 Kelvin times the natural log of 1 times 10 to the negative 6. In this case, you get a Gibbs free energy change of approximately 34,228.9 joules. Well, your answer isn't quite finished yet because that is too high a number of significant figures. So that becomes simply 34.2 kilojoules, fitting your significant figure requirement of about 3, because on the AP test, as Warner's most likely told you, they accept significant figures within plus or minus 1. Therefore, 3 is almost always a safe number because very rarely is there less than 2 or more than 4 significant figures involved in a problem. Next, you have the solubility products, your KSP. Given that A, big B, little b, meaning your atom, for a molecule, your atom of A, then this little a equals the number of it, then big B, then B equals the little number. Say something like CaCl2, A is this little a of 1, this little a would be equal to 1, but this little b would be equal to 2 because that's the number of Cl's involved. Now it's just an example. Then your KSP equals the concentration of the A positive ion to its coefficient times the concentration of B minus the negative ion raised to its coefficient. Moving on with example number 6, finding your equilibrium constant for a weak acid. Now you may remember from general chemistry that a weak acid is something that does not completely dissociate. So for the purpose of just the generic example, I'll use hydrofluoric acid because that is a weak acid because the electronegativity of the fluorine will allow it to not dissociate much in solution. So your general formula for a weak acid is HA. H obviously being your hydrogen, A being the other atom or molecule, in this case, like I said, fluorine. Then you set up what's called an ice table. And an ice table measures your initial concentration, your change in concentration, and then your end concentration. So you write out your equation, your base equation, HA plus water yields, or is in equilibrium, a hydronium ion, H3O with a positive charge, and A minus, the negative ion from your weak acid. So, your initial concentration is X for HA, and your initial concentration for hydronium and A minus is 0. The water is left separate because it is given that it's not going to affect or be it's a pure liquid. That's why it's left out. Your change in concentration is minus little x, and then your change in these is going to be both plus x and plus x because this plus x from the H and this plus x from the A negative, or the negative ion. Your end concentration is big X minus little x, and your end concentration for these is 0 plus x. So your Ka equals the concentration of your hydronium ion times your concentration of your negative ion that barely dissociated from your weak acid over the concentration of the weak acid initially, at the end, but the initial weak acid, the formula for it. So here's an example. We have a solution of HC2H3O2 with an initial concentration of 2.7 molar. After dissociation occurs and equilibrium is established, the concentration of C2H3O2- is found to be 1.1 molar, so they want you to find the Ka. Well, you know your initial concentration of this weak acid is 2.7 molar. You know that you don't care about the water because it's a pure liquid, and then you know that the initial concentration of your hydronium and your C2H3O2- ion will be 0 before the reaction occurs. You know that the end concentration of your C2H3O2- is 1.1, and because this is a monoprotic acid, meaning it has one hydrogen to dissociate from, that means there is no multiplication involved. You have 1.1 molar here and 1.1 molar here, meaning that there is a change of 1.1 here and 1.1 here, meaning it decreased 1.1 molar here, leaving you with an end concentration of 1.6 molar. So your Ka, your concentration of hydronium times your concentration of the negative ion divided by the concentration of the weak acid is equal to 1.1 times 1.1 divided by 1.6, meaning you have a Ka of 0.756.